All right, welcome back, everyone. First, we'll start. Are there any administrative announcements from the TAs? Timeline for the midterm? I think should return. Yeah, so the midterms have been graded. We'll return them today. And I said it before, I'll just say it again. If you're not, much of the class did very well. There are some people who didn't do as well, and I understand some people are taking the class pass fail. If you feel like you didn't perform to the level that you were hoping, then please see the TAs. A lot of the concepts build on each other, so it's important. There are things that you don't really have clear in your mind in terms of your understanding to get those ironed out. And we are here for you, so please come see us.
So,
One more.
I'll be traveling throughout. So I don't know, say, if you have any questions, but I'll be reachable through email.
Yeah, Wenji will be out of town, as he said. So if you have questions that you want to discuss in person, myself or Annabelle are the people to ask. Also, if you are if you are tracking the calendar, you will notice that we also have a class tomorrow, which is different from our normal cadence. And the reason we'd have that is because one of our classes this year falls on Juneteenth, which is a federal and Scripps holiday. And we scheduled it this way in conjunction with the the heterocycles class, because our understanding is they aren't meeting tomorrow. But it's not part of the normal class schedule. So if you cannot make it for some reason, just let the TAs know. As always, the class video recordings will be available. We don't really want to miss the class period, but we understand that this is not the normal class cadence that you signed up for. So we will work with you on that. Same time, same place, one extra class period this week. Any questions? Okay, let's jump into it. We've got quite a bit of ground to cover. Topic near and dear to my heart. The theme is metal mediated and catalyzed additions to pi bonds, which my group has had a lot of fun with over the years. We'll start out with a little bit of a tangent to cover a topic that otherwise doesn't really fit in super well anywhere else. And that's a set of rules called the Green-Davies-Mingus rules, named after Malcolm Green, Steve Davies, Michael Mingus, three Oxford chemists of great notoriety. And these rules apply specifically, they are a framework for predicting additions to organometallic complexes that have multiple potential sites. So pi systems, multiple pi systems that are inequivalent, coordinated to a metal, and particularly an 18 electron complex. So I want to draw this distinction very clearly. Most of the rest of the lecture will focus on D8 16 electron complexes, palladium, olefin species. And that is different from what we're covering here, which are 18 electron. So this is a framework that will be useful in some contexts. Much of what we will cover will not directly fall out of these rules. So I just want to make that crystal clear. Okay, here are the three rules. You can read them yourself. I'll read them very quickly. Nucleophilic attack is preferred on even numbered polyenes. Here I put polyenes in quotes. This really just means anything that has multiple CC pi bonds, benzene, their aromatic systems, allyl groups, CP rings, those are all called polyenes in this framework. Even number is preferred to odd numbered nucleophiles, preferentially add to acyclic over cyclic. And then rule 3 is actually two different rules. One is that for even hapticity, acyclic polyene, so think of 1,3-diene bound to an 18 electron metal complex, nucleophiles will attack at a terminal position. And then for odd hapticity, so think here like allyl fragments, nucleophiles will add at a terminal position if the metal is highly electrophilic. Otherwise, they add at an internal position. So what is categorized as highly electrophilic? Let's say cationic metal species in relatively high oxidation state. I think you hopefully have some kind of intuitive idea. And then here is the order of reactivity, where you can see the extent of steric hindrance plays a role, as does the number of pi bonds in the overall conjugated system and whether the system is aromatic or not. Okay, let's, I think the best way to, in the abstract, I think these rules are not that intuitive. So the best way to do it is just apply them to some case studies. So we'll warm up our minds today with problem of the day number 1 from the worksheet, which is really just meant to apply the concepts that we just covered to a few specific cases, and also give you a flavor when we talk about the category of complexes to which these rules are relevant, what those look like. So let's take a look. And I think we'll do this by vote. So I'll give you 30 seconds to look at A, B, and C, each of which have a couple different positions, which are outlined here. And I will just take a straw poll of the class for what your preferred site of addition is based on these rules, and then we will check our work together. And if you do it really quick and you are bored waiting, then I would encourage you to get some electron counting practice on each of the 3. All right, first up, A. We've got 4 potential sites. First 2 are on the bound diene, terminal internal. Number 3 is an allyl position. I guess there could be actually, maybe I should draw this. I don't think anyone's going to vote for this now because I didn't even draw it at the start, but there is a 5th potential position, which is the internal position of the allyl. Maybe I'll renumber this just so it's a little less. Okay, so there are 2 positions on the allyl, internal or terminal, and then there is the possibility of adding to the benzene. All 6 carbon atoms in the benzene in this case are equivalent. Okay, so let's, with a show of hands, applying the rules we just covered, who favors number 1? Okay, I think that is a vast majority. Number 2, any takers? Julian? Anyone else? Number 3? 4? I don't think anyone's going to guess 4. That's fine. 5. Okay, so Julian, you are the contrarian on this one. Why did you think 2 in this case?
I'm not sure I want to talk about it because if I'm the only one, but I didn't know about the electrophilicity of the metal and whether that would affect the internal versus the terminal position.
I see. Okay. Well, let me add a.
Maybe if it's cationic.
Yes. Let me emphasize this. This is a good point. I'm glad you are making this distinction. Let me just emphasize this period. So this has 2 parts. The first part is that nucleophiles preferentially add to even hapticity acyclic polyene ligands at a terminus, period. And then the next part is, and so this last clause of if a highly electrophilic, if metal is highly electrophilic applies to the second statement. So this is we would say an even hapticity acyclic polyene. So the first sub-rule within rule 3 would apply, which would say should add at a terminus.
Yeah, that makes sense.
Okay, so we're all in alignment there. One is the winner. How about B? Same thing, straw poll, 1, 2, a few takers, 3. Okay, I don't think any had a majority. There are some undecided voters, I think, but the plurality was 2. So let's hear from one of the people who said 2. What do you think? Funny.
Well, we have different of opacity here, opacity 2, opacity 3. So we will go for the even one, which is opacity 2. And doesn't matter, I mean, it does matter that which side will be attacked, but because we only have 2 on that molecule, so maybe just because there's 2 carbons that can be 2, right?
Yeah, so this one is a little bit, I think Mahdi's pointing out there are technically the 2 alkenyl carbon atoms are inequivalent in this case, as are the 2 positions of the but I think it might be hard for people to visualize like the transannular ring strain and whatnot. So I tried to simplify this one by limiting the number of choices. Okay, so Mahdi applies, the main rule that is applied here is that nucleophilic attack is preferred on even numbered polyenes. And we've got a couple odd ones and only one even one. And I've stacked the deck so that there's only one site that you can pick here. All right, last one, iron CP biscarbonyl ethylene complex. 1, 2, 3. Okay, everybody got 3. Odd versus even, carbonyl, no takers. There probably are some conditions where you can add to the carbonyl, but you'd have to be an adventurer to pick that, given that this is all addition to CC pi bonds.
Question.
Please,
On the rankings of the.
Yeah. go back up.
Why is the cyclobutadiene less reactive than benzene? Aromatic. Oh,
Why is cyclobutadiene less reactive
I
than
thought,
benzene?
wait, it's more. It's literally.
Shows number 1.
No, like the format member.
I think your question, okay, so Riku, your question is about this here, is that right? So, yeah, so I think if I am hearing you correctly, you're uncomfortable with the fact that you have an
Aromatic
aromatic and an anti-aromatic.
and the aromatic being
The
more reactive.
anti-aromatic, you know from your experience working in the main group that anti-aromatic compounds in general are much more reactive. So remember that implicitly what we have here in each case is the metal complex. But the reactivity here of the bound organic fragment is different than the free Alex.
Is the whole like even and odd hapticity thing sort of just a slight abstraction from like the even hapticity ligands are, you should think of them as sort of the neutral species, whereas the odd hapticity ones you should think of as the anion, which is why they're less reactive towards nucleophilic attack. Right, because the allo ligand, we think of it as an allo anion. So is that why, like, at a sort of a first approximation, all the odd hapticity ones are less reactive than even hapticity ones?
Because they have more electron density, first approximation. I think that is a reasonable way to think about it. And certainly if just as a like mnemonic device, that's useful, I think. I don't have a lot of objection to that. But I would point out that it might be a little bit incomplete as a, if you play that out, because you'll see here the ordering at the end of tropylium, which we would know is cationic in its free form, being less reactive than the anionic fragments. So it's not a one-for-one translation of that idea. Okay, let's now get into the main thrust, my favorite topic in organometallic chemistry, additions to alkenes. And we're going to tell this story predominantly through the lens of palladium. Other metals promote additions to pi systems as well. But the history really runs through palladium. So that's how we'll tell this story. So there are two general mechanisms, and they go by different names. So I think the most clear and unambiguous way to describe it as an outer sphere mechanism, number one, and number two, an inner sphere mechanism. But you will also hear terminology for the former, like nucleometallation, emphasizing that this resembles a nucleophilic attack, or Wacker type. That Wacker type nomenclature is especially confusing because, as we'll see, the Wacker process and its related reactions actually have a lot of mechanistic diversity, but in the literature, people use that terminology. So I want to explain that to you. And the other will also be referred to as migratory insertion or Heck-type addition. What is the difference? In the outer sphere, it looks kind of like what we covered in the Green-Davies-Mingos rules, and that's why those go nicely together. So you could imagine this being a preferred pathway when you have a coordinatively saturated metal, because the nucleophile doesn't need to get on the metal center first to be added. The inner sphere is the opposite. You need a free coordination site to associate your nucleophile, which then becomes a migrating group in your 1,2 migratory insertion. Consequences here in terms of the coordination number is that a migratory insertion, as we've already covered, opens up a coordination site, and then you typically need a trapping ligand so that it doesn't go in the reverse direction. That's less true because the reactions are intrinsically less reversible when you're migrating in an aryl group, for example, but it can be reversible when you're migrating in a heteroatom-based group. And then in the outer sphere case, just like we saw in these rules, they work for 18 electron metal complexes because you don't need to have a free coordination site. Same story here. So your coordination number remains the same upon alkene addition. But you do have a swap of an L-type ligand for an X-type ligand, so that charge needs to go somewhere. So that's why I've drawn this as being anionic. We'll have a quick refresher here on a concept we covered before in the back bonding portion of one of the earlier lectures, which is that metal olefin species in general have a spectrum of reactivity depending on their extent of back bonding. With late transition metals in relatively high oxidation states, metal-bound olefin complexes are electrophilic at the metal. With early transition metals in lower oxidation states, metal olefin complexes can be nucleophilic at the olefin because of the extreme extent of back bonding. And they can even, in some cases, be thought of as 1,2 bis Grignards. To me, the most illustrative example that resonates, I think, with the organic community is the Kalinkovich reaction, where you have a olefin low valent titanium adduct that acts effectively as a 1,2 bis Grignard in its addition to carbonyl compounds. That's very different than what we'll talk about today with palladium, where the olefin generally can be thought of as electrophilic. And this can be then thought of as a form of umpalum, because we know that many olefins, not the electronically jazzed up ones like Michael acceptors, but many olefins, alpha olefins, are nucleophilic. So upon coordination of palladium-2 or platinum-2 or gold-1, that is a form of umpalum where the alkenyl carbon atoms become electrophilic. Wacker oxidation. We've covered some very historically important reactions who had their origins in industry, the Monsanto acetic acid process, hydroformylation / the OXO process. And Wacker oxidation is one of this that fits in this category. It's a name reaction, but the name is not a person, it's a company, Wacker Chemie, a German company. And the historical origins of this, for if you're a chemistry history enthusiast like I am at times, I think very fascinating. So it dates back to the 1800s. And a lot of what I will recount here can be found in this Angewandte account if you're interested in reading more. So put yourself back in the minds of a chemist in the 1800s. Many of the tools that we take for granted, IR, NMR, UV-Vis, were not really online at that point. And so structural elucidation was much more of an art than a science at that point. And a lot of the focus was not on, just determining what functional groups are present. So you have an organic extract, you want to know what the main components are, you want to know what functional groups in general are present. And one test that was used at this period of time was called the Phillips olefin test, where you could take your organic extract, shown here creatively as question mark, question mark, question mark. And if that organic extract contained, and then you would treat that extract with palladium dichloride in water. And if it contained an olefin, you would see as your highly quantitative, that was a joke, analytical readout, formation of palladium black. And then from that, you would infer that you had an olefin in your organic extract. And the byproduct at that time, folks paid less attention to, but was the corresponding carbonyl compound, in this case, methyl ketone. Of course, as a synthetic method, this is a bit of a fixer-upper, uses an equivalent of palladium-2. You can imagine it's not atom economic, it's not perhaps going to have a lot of chemoselectivity. So if you wanted to use this as a means of making carbonyl compounds from olefins, you'd need to solve some problems. And the main problem you need to solve is how to turn this over catalytically. And that was the innovation from Wacker Chemie, and a team led by Walter Hafner in the 1950s. And what we now refer to as the Wacker process refers specifically to the conversion of ethylene to acetaldehyde, promoted initially by palladium-2, just as we saw in the Phillips olefin test, that generates palladium-0, aka palladium black, as byproduct. But now in the presence of copper-2 salts, you can get back to palladium-2, you generate reduced copper, and copper has this nice ability to be oxidized by molecular oxygen. That can be a pain when you're trying to reliably keep something as its copper-1 counterpart, for example, in cuprate type additions. But when in this context, you can couple it with aerobic oxidation, so the overall process is turned over by O2. So what you've done is you found a way to take ethylene and O2, and your only stoichiometric byproducts are water. Not bad. Along with some parallel discoveries that we saw in hydrogenation, hydroformylation, this really, the discovery of the Wacker process really captured the imagination of the community, because it showed that homogeneous catalysis could really rival heterogeneous catalysis for industrial scale commodity chemicals. applications. Some interesting historical context that motivated this work by Wacker Chemie. So if we think about the time in world history that this work was happening, this was post-World War II Germany. Germany as a country was rebuilding after the war. Wacker Chemie was headquartered, geographically co-localized with a number of interesting research institutes and companies, including so in the so-called Ruhrgebiet region, which is like the equivalent of it's a coal mining region of Germany, the equivalent of like Pittsburgh in the United States. Home of the Max Planck Institute for Kohlenforschung and other prominent areas of chemical research. And so at that time, a lot of the themes coming out of German organometallic research were new ways to use petrochemical feedstocks. That was the genesis of discovery of nickel cod and many other key discoveries from that period of time. So a lot of the industrially important compounds, or those are becoming important, like vinyl acetate, vinyl chloride, these types of feedstocks that people are now plugging into polymerizations in the 50s and 60s. They would ultimately be sourced from calcium carbide, which is expensive. And calcium carbide would be converted to ethylene, acetylene, the higher oxidation form of ethylene, and this was not ideal. So much research was focused on how to make these types of products, substituted C2 building blocks from ethylene, which was cheaper and became much more cost effective when a new refinery called the Esso refinery came online in the region. So the Wacker Chemie team performed this somewhat skeptical somewhat suspicious looking and mechanistically ill-defined reaction where they were taking palladium on carbon, O2, and ethylene and hoping to form ethylene oxide. And I'm not sure if they had a clear mechanistic hypothesis here, but you could at least in your free time draw some things out that might be not totally unreasonable. And as the story goes, when they opened the reactor, they knew immediately they had not made ethylene oxide, but instead they knew they had made acetaldehyde. How? They smell, just like in the hydroformylation. You know by smell when you've made an aldehyde when you didn't expect to. The mechanism of Wacker process has been studied at length, but some mysteries still remain. This is not a totally closed book in terms of mechanism. And at a high level, I would say what makes this system challenging to study mechanistically, it's not unlike the Heisenberg uncertainty principle, which is that to get some mechanistic insight, you normally need to perturb the system away from the industrial relevant conditions. And we'll see examples of that. And then making that perturbation, you're left with a question of whether that is the insight actually holds for the true system. And so the conditions you can imagine, you've got mass transfer considerations because you've got gas-water interface stuff going on. You've got both in terms of the ethylene in and the O2 as regeneration. There's a lot going on that makes this a really difficult system to do inline. So I'm going to try to summarize what is known at present, and maybe the next time I give this lecture, it will change and I'll have to update this, but I'll try to give a flavor for this. So there are, the prevailing belief at the moment is that there are two general operating regimes, and they are divided based on the chloride concentration. So there's the industrial relevant conditions, which are the low chloride concentration, and then there's this other set of conditions, which are the high chloride concentration. Why is that important? Because the chloride concentration affects the preferred coordination environment around palladium. So in these two different regimes, it has empirically been found that there are two different rate laws. And the key difference between these two rate laws is the presence or absence or let me reframe that, the order in the denominator term of the chloride counteranion. So the catalytically active, so let me unpack that. So the catalytically active species is this palladium tetrachloro bisanionic salt that is formed in situ from a palladium-2 precursor and then some chloride salt. This is believed to be the resting state. And so if we know this is the resting state and we know this is the rate law, then we can apply some of the lessons that we have learned in this class or from Donna or from your previous life taking phys-org classes, which is if this is the resting state and this is the rate law, and we know we have these terms, we know we have a ethylene term in the numerator and a proton and a chloride to the power of 2 term in the denominator. That means in going from the resting state to the transition state, turnover limiting transition state, we're going to need to lose 2 equivalents of chloride. We're going to need to gain an equivalent of the ethylene. And we're going to need to lose an equivalent of a proton. That looks a little odd at first glance. Where's that proton coming from? And why isn't there a water term here? Because we think that the transition state should involve water as a nucleophile or hydroxide. The solvent here is water. So you always have excess water. So that doesn't show up in the rate law. This is sort of a saturation kinetics version. But the loss of a proton from the bound water does. So what is that telling us? That's telling us we had a water bound, but then we lost a proton. So just from it's kind of like there's some parallel here to retrosynthesis. It's like just from the resting state and from the rate law, we can piece together what components need to be in the turnover limiting transition state. And so if you drew this kind of addition as your transition state, that would be good. It's a little bit more subtle than this, so I'm just going to draw this as currently understood, but I think you probably wouldn't have any reason to think that it's anything other than the CO bond formation, unless you had some DFT, which this DFT study here is the one that that points me to draw this, is actually it's turnover limiting transition state. Somewhat unusual is actually a bond rotation. So it's this, what's happened here is you've had a 1,2 migratory insertion into the olefin, and now because you have this dangling coordinating ligand in the hydroxide, it can come back around and continue to chelate. And then you have a rotation about this bond where that needs to dissociate, and that turns out to be turnover limiting. Every step leading up to that turnover limiting transition state is reversible. So then that transitions, you get all of those terms in the rate law. Yeah.
Can I ask a clarifying question?
Please.
It says like low chloride concentration, low copper chloride, high. What is that in respect to? Like relative to?
Yeah, I think relative to the range of conditions in which the reaction can still turn over. So this is, so you can, and we'll see examples of this, you can juice up the amount of chloride and copper chloride in solution and it will still,
Oh, I see.
but those are not the industrially relevant conditions. Yes.
Would it be reasonable to propose for example, palladium hydroxy dimer that forms at first with the equilibrium between the hydroxy dimer and the tetrachlorate, and then the hydroxy dimer binds with ethylene? Would that give the same rainfall?
If you had a change in nuclearity between the resting state and the transition state, you would see a partial term. You would see a non-first order behavior in the metal. So it's possible if you rest as the monomer, you go through a dimer, the turnover element transition state is a monomer. The kinetics would not allow you to rule that possibility out. But if the resting state's a dimer and the turnover element transition state is a monomer, or the vice versa, then you would see that in the term for the metal catalyst in the rate law. Hopefully Donna's not watching. Or hopefully I got it right. It's even better, I got it right and she is watching. And then let me just take a minute to do the charge inventory. Yeah, so I think we're all right. Here we've got X type, X type, X type, X type. And then we can apply this exact same logic and I'll go through this more quickly. In this case, now the difference is we don't have that proton term and we don't have the to the power of 2 and the chloride in the denominator. So we bind an ethylene, we lose 1 chloride, and then now our overall charge is -1, right? So we've swapped an X type ligand for an L type ligand. And then we have the water coming in. And I realized probably shouldn't draw, should probably take better care here. If I'm going to draw this as a transition state, I should probably draw some real partial bonds. Okay, any questions on this?
For the second transition state.
Yeah.
You have a negative order in the chloride because it competes with alkene binding.
Correct.
From the resting state.
Yes, exactly. So when people talk about the dichotomy in the Wacker addition, this is what they're talking about, this syn addition versus anti-addition. And it's dependent on a number of factors that still, I think, we're still as a community teasing this out. It's dependent on the nucleophile, it's dependent on the conditions, it's dependent on the ligand environment. But again, what we know in the context of the Wacker process is that this dependency of high chloride, low chloride. And in terms of a mnemonic, I like to think of this as when you have high chloride concentration, you've got a lot of chloride around that's competing for binding to the metal. So the metal is like struggling to get a chloride off, and it's definitely not going to get 2 chlorides off. So it gets 1 off, and then it finds the olefin, and then the reaction takes place. And the only path by which it can take place is this outer sphere attack. And then in the low chloride, the metal is kind of more agnostic and free to sample. Okay, it's got a water on, it's got a chloride on, it's got an olefin on, because the chloride's not competing as strongly since it's in lower concentration. The high chloride and particularly high copper 2 chloride, in addition to the products, can lead to formation of some byproducts, and we'll come back to this in a moment. And the high chloride, copper 2 chloride, in terms of its reaction with organopalladium salts specifically, kind of behaves like a Cl+ source. And so this alkyl palladium bond can actually get converted to an alkyl chloride bond. The mechanistic details here are not super well understood and are not that important, but I just want to make that point because we'll talk more about intercepting these types of intermediates through other pathways besides the canonical beta hydride elimination, which leads to the acetaldehyde product. We'll now discuss two important mechanistic experiments, and also this gets back to this point I made about to understand mechanism, you make some perturbation from the real system, and then that perturbation, and you're left with this question, did that perturbation change something really meaningful? So these are experiments from two giants in the field of organopalladium chemistry, John Stille and Jan Beckvall. Let's look at the Stille example first. And we'll get some. So what Stille does, so we're taking, in both cases, we're taking a labeled starting material. So D2Z configured D2 ethylene. Palladium 2, we make the oxypallidated intermediate. In the Stille case, we do that in the presence of CO. So what do we expect might happen in the presence of CO? Gift, I don't think I've called on you yet. What do you think? Alkyl palladium plus CO. All right, first things first, we're going to coordinate CO here, right? Surely this has to be the first step. And then what? Metal carbonyl complex, alkyl ligand. What do you think? All right, assist from collaborator Al.
1-1 migratory insertion.
1-1 migratory insertion. Very good. Now we've got an acyl palladium 2. And are you happy stopping here?
That's an electrophilic side. So if you have with an exogenous one, it would add into it. Otherwise, it would cyclize.
Al's saying this is highly electrophilic at carbonyl. So if we have some exogenous nucleophile, that might add in, but I'm not seeing any, but we've got this endogenous tethered alcohol. So you said that was going to cyclize. What is the product from the cyclization going to be out?
Cyclic ester is lactone or
Lactone. And then help me on the stereochemistry of deuterium.
I think it should be syn.
Yeah, okay, they're, or cis, they're in a trans relationship in the open chain. That means when you wrap them up in a cycle, they're going to be cis. So what did that whole experiment allow us to read out in the end? Why go to all that trouble? What did it actually teach us? Al?
The mechanism for, I guess, since you label with deuterium your substrate, it should tell you whether syn or anti addition happens.
Beautiful. See, we went to all that trouble because it allows us to read out this relative stereochemistry. Are these either the same side of the pi system or the opposite side of the pi system? Those would give opposite deuterium stereochemistries. Okay, similar concept, different execution here from Beckfall. What do we think here? I gave this hint about how copper chloride likes to react with alkyl palladium. Sebastian, what do you think?
They observe the trans
Sorry.
atom. Oh, no, never mind, because there's no carbon monoxide. So copper. Right, so here.
So what do we say up here? When we have a lot of copper chloride around, we can convert alkyl palladium to
Yeah.
alkyl chloride.
Right, so then you would assume that you make that, and I don't know if you would get an oxetane out of that.
Okay, I
You
think
could,
you're,
you
all right.
heat it, and then-
You're on an interesting track here. So I'm gonna give you this information that you might not know otherwise, which is that conversion of alkyl palladium 2 to alkyl chloride is stereoinvertive. And that's a story for another day, but in the field in the 1970s, that was already well appreciated. So we know that's invertive. So this is the intermediate we're gonna get. And then you said something wise, I think, about a cyclization. But let's count the number of atoms involved in that putative cyclization that you proposed. 1, 2, 3, if the chloride's a leaving group. So what would your actual product be?
Oxirane.
Oxirane or oxide. And how about, give me something on the stereochemistry?
You would, I mean, they would be cis as well, wouldn't they?
This as well. Great. Any questions on that? So the Beckfall case, so the Stille case, we get some supportive evidence for an anti-addition, anti-oxypalidation, but then we're left with this question of, well, we added CO, there's no CO in the catalytic system. What did that change? And so the Beckfall system gets us closer to that because we're just trying to intercept an intermediate that we know is actually, or a byproduct that we know is generated in the true system as well. And so, again, this gives you a little bit of a flavor for why this type of mechanistic work is hard. But even still, in the Beckfall case, you need to perturb it away from the industrial relevant conditions in terms of the operating pressures, and you obviously cannot use the same pressure of a very precious D2 ethylene as you use in your normal ethylene stream. Okay, so we've talked about the first step, oxypalidation. Let's talk about downstream steps. That brings us to problem of the day number 2, where we're given 2 pieces of data, both pertaining to labeling. Let me share that in case you don't have the information handy. Okay, here we go. So first experiment, we're taking Wacker process conditions, but we're doing it with D2O. And we see that there's no deuterium in the acetaldehyde product. Bless you. Second experiment, we're taking D4 ethylene, and we're seeing exactly 4 deuteriums in the product. We just covered that the first steps, I think hopefully you have an appreciation for this. It's going to be ethylene coordination, it's going to be oxypalidation, and then and then what? So take a minute to think about that. Well, we know that it's going to be a beta hydride, or in this case, beta deuteride elimination in the case of the second experiment. So I'll give you that one. But then think about, from this intermediate, what are these labeling experiments telling us about the mechanism? All right, Mike, what do you think here? Let's first just consider in our strong inference workflow, like what is actually possible? What are the mechanistic scenarios that one could consider here?
Yeah, I mean, since you don't have any CO, it's not gonna be like your usual migratory insertion. It has to be like, the alcohol. You need to oxidize it technically.
Okay.
To result in but I was thinking that, maybe in like a concerted fashion, you get a sort of like assisted beta hydride elimination.
Okay, all right, so you got the beta hydride elimination done. So you've got a olefin bound palladium hydride / deuteride here.
Yeah.
And if you squint, you can view this and just say, hey, we're already done. We have the enol form of acetaldehyde, and it's gonna dissociate. Thank you. So we've got the enol bound form of acetaldehyde, and then all that needs to happen is the palladium 2 hydride or deuteride falls off, and that's going to react with base to generate palladium 0 plus EB in this case. And then this is just going to get hydrolyzed, or this is going to undergo, not hydrolyzed, sorry, this is just going to undergo tautomerization. But what's the problem here?
You have all of your deuterium is still incorporated, but you're in water. So that's the odd thing.
So this would not get you to the D4 product.
Yeah.
Because tautomerization in water is going to involve incorporation of a proton at the alpha position, not a deuteron.
Is it instead like the palladium? It does decoordinate, but is it electrophilic enough where it's like an actual like attack on the palladium deuteride? So instead of like a normal detomer, like just in water, you kind of use that like an enolate.
I like where you're going, but I think you might not need to have as creative a solution as the one that you proposed. So what we did to get here was a beta hydride eliminate, a beta.
So you just do it again.
So you can just do the microscopic reverse, as Mike's saying, but you're gonna do it, not the true microscopic reverse. You're gonna do it in the opposite direction. So you transfer your deuteride, you do it, so it's a 1,2 migratory insertion. You made a new carbon deuterium bond, carbon palladium bond. And then now look what we have here. I'll redraw this in a more suggestive, and I'll draw this in a more suggestive way. Now what do you have? You have an H atom, beta to palladium. It's not the canonical beta hydride that we're used to, but it's more thinking back to that transfer hydrogenation lecture. It's still a beta hydride elimination. It's just that we're eliminating a hydride from a beta, a hydroxyl group. Get us now. And then this will be a very weak interaction with the palladium hydride. And that's going to go further to make palladium 0 plus H. So together, taken together, these experiments allow us to conclude that the beta hydride elimination step and the conversion to product involves an initial beta hydride elimination, but then a reinsertion and a beta hydride elimination out through the alcohol, which is irreversible. And then the resultant palladium 2 hydride is quenched. Questions on that? And this is a common theme if you're familiar at all with the field of migratory heck type additions as first developed by Larock and then really taken to new heights by Matt Sigmund's group. These reactions also often will migrate through chain walking through an alkyl chain until they find an alcohol, oxidize that alcohol to the corresponding carbonyl. And this is the same concept. And this is what guides that selectivity. They do the final reductive beta hydride elimination through the alcohol. So everything we've talked about so far, we would bin within under the auspices of the Wacker process. But for most people in this room, you're not working with a reactor. You're not chemical engineers, so you're not working in a reactor. You're not working with ethylene, and you're hopefully not completing any total synthesis of acetaldehyde. So how do we apply this to more interesting molecules that we care about? And the key development here was from Jiro Tsuji. Jiro Tsuji made many key contributions in organopalladium chemistry that we'll cover in class. In the context of his work on Wacker type additions, he made this discovery that similar to the Wacker process, but a reaction performed in DMF and other amide solvents work as well here. You can extend reactivity to other terminal olefins. And this is so reliable in terms of its Markovnikov selectivity for methyl ketone that it's often said that methyl ketones are a key signaling element or synthon for olefins via the Tsuji-Wacker addition. In terms of origins of regio selectivity, we've got two main factors to think about, steric and electronics, and they both operate in the same direction here. We put the metal on the less hindered position, which is good. And in terms of the electronics, remember our reaction mechanism is electrophilic, and we accumulate delta plus at the more hindered secondary site where the nucleophile ultimately attacks. What about if you want to invert selectivity and you're not interested in making methyl ketone, but you want to make aldehyde out? And you'll note here that this is a different disconnection strategy than making terminal aldehydes via hydroformylation, because your number of carbon atoms is different here. So what if you wanted to achieve an aldehyde selective Wacker addition? This is still somewhat of an unsolved problem. The significant advances were made in the Grubbs group, building on prior work from Feringa and others. And this was close to the time that I was in the group as a postdoc. This particular paper from Zach Wickens, first author, a name you might recognize, published in 2013, a few months before I joined as a postdoc. So what's going on here? It's complicated. It's a complicated gamish of additives here, but the key ones to draw attention to are the addition of silver nitrite, and then this solvent mixture of bulky tertiary alcohol and nitromethane. The nitrite is thought to be the key player here, and I think the mechanistic details are a little bit murky, I would say, at best, but what they draw in the paper at least is they invoke the addition, the propensity of radicals to want to add to the terminal position of olefins. And so they say that this type of species is guiding addition of oxygen to the terminal position, and they support this through using labeled nitrite and seeing that the O18 labeled is transferred with high fidelity to the terminal position. This mechanism could be wrong, so I don't want to say too much about it, but this is what is proposed in the paper at least. Internal olefins are historically more challenging in Wacker type additions. I think that largely stems from the fact that you are forced to put the metal on a less favored secondary alkyl position. And so to juice up reactivity, what is needed is typically in situ formation of a bis-cationic palladium-2. In this particular example, also from Grubbs, based on earlier work from Canada, they do this through the combination of a palladium-2 pre-catalyst and HbF4 as an additive to make the bis-cationic palladium 2 bis-acetonitrile bis-BF4 salt active form of the catalyst in situ, and that allows them to achieve reactivity with internal alkenes. What about styrenes in Wacker oxidation, and what about other oxidants? So I kind of skimmed through this, but we looked at O2 as the main terminal oxidant. In the internal alkene case from Grubbs, we've got benzoquinone as a terminal oxidant. But other oxidants can be used here. O2 is a pretty good one, but it's often not trivial for people not operating in the commodities chemicals space to use O2 conveniently, because if you operate above 5% O2, you have in an organic solvent, you have this risk of combustion. So there are ways to work around this. You can keep your O2 loading below 5%, but in general, there are some advantages of O2, there are some disadvantages, and so other oxidants are sometimes welcome to consider, and a good one is TBHP. That's been used recently to great success by our colleague Jin Kwan. So here's an example from Matt Sigmund's group. He is looking to extend Wacker type reactivity to styrenes. You might think styrenes are an easy class of olefins to develop catalytic functionalization chemistry, but in the context of Wacker additions, they're more challenging because they're prone to polymerization, they're prone to oxidative fragmentation byproducts. So this had been a challenge for a period of time before the Sigmund group took this on, and they found that TBHP works as a uniquely effective oxidant in conjunction with this carbene ligated palladium-2 pre-catalyst shown here. The ligand here is IPER. Just one reminder for nomenclature, the NHC ligands, I don't think we talked about this in much detail before. They have this system where I, which stands for imidazole or imidazolinine, means the saturated backbone. Sorry, it means unsaturated backbone. If you see S, that means saturated backbone. So if you see the ligand CyPER, that means that this is saturated with 2 methylenes. If you see IPER, that means it's unsaturated as the imidazole. This is the pre-catalyst. These are the reaction conditions. So you can infer what's happening in situ is what? We've got a silver salt, we've got some chloride counteranions. What's going to be generated in situ? Pierre, what do you think?
Cationic palladium species.
There you go. So you're gonna salt metathesis, generate a bunch of silver chloride, put these triflates on. The triflates are going to be weakly coordinating. So in the reaction conditions, you're probably going to coordinate something else, maybe water from the TBHP, because normally TBHP comes in aqueous solvent, maybe methanol. You've got a cationic palladium-2 that should be hot to trot for electrophilic alkene additions. So this is the reaction. And then problem of the day number 3 asks you to consider a few different things. So 1, can we pin down the O atom source? Why is that important? Let's count the different O atoms that we have here. We've got oxygen, methanol, we've got, okay, triflate. That's not a really good candidate, but I guess we shouldn't rule it out a priori. Or we've got the TBHP. So question number 1, which of these is getting into the product and how would we determine that? Thoughts, Sebastian?
Could you maybe swap out TBHP for something like benzoquinone, something that worked in another system? I mean, I'm sure that this was tailored exactly for what they needed, but maybe there is something else that just, is not explicitly an oxygen containing oxygen. I
Okay.
mean,
I like that. So you run this experiment, let's say from your screening, you know, there's some other oxidant that works to some extent. You swap that in, and what would that tell you? How are you going to read out that data?
Well, actually, I guess that would only work if you also had some form of labeling oxygen, because I guess my whole goal was to see, like, well, you could run these two experiments, one of them gets you a labeled oxygen, one of them doesn't.
Okay, so let's go to label oxygen. What do you want to label?
Maybe we start with methanol. That sounds reasonably commercial.
Label the easy stuff first and see what happens. That's not a bad way to go. So let's label methanol. Let's potentially label the water. I mean, and what's the caveat or point that you need to be a little bit concerned with in these types of labeling experiments when you're generating a ketone product? What was that, Pierre? Exchangeable. So you have to be very careful about these because secondary processes can can convolute your data. So let's play this out. Imagine a hypothetical scenario where 100% of your label initially came from TBHP, or 100% of your oxygen initially came from TBHP, and you used O18 labeled water, and you saw O18 in the product, and you made the wrong conclusion because what happened was this O16 product was formed under the reaction conditions, and in a sea of O18 water, you just exchanged it out. So these reactions you need to monitor very carefully at low conversion to try to get at the true O18 labeling source. And that is indeed what they did. They used these same labels. It would be better, it would probably be cleaner if you can label the TBHP, but then you are in this issue. You run into this issue where you need to make that somehow. And you probably want to make it with O18 in only one position. And most people don't want to have a whole PhD project just devoted to this. So that's not. So they did what Sebastian suggested, label the things that are easy to label first. They found that they couldn't get in any label at early time points that way. At late time points, secondary processes dominate, so they can get label in. So from that, they had some supporting evidence that TBHP was the oxygen atom source. Okay, so that's step one. We know that the initial oxypalidation is going to involve TBHP, and then we're going to need to consider what happens next. So let me draw that out. Well, you draw it out yourself and then think about downstream scenarios for what might happen next. I'm going to draw this as the chelate structure. I'll draw this with the dated interaction so it's crystal clear what I mean by this. And these will both be open coordinations. One of these will be the cyper ligand, and then you'll probably have an open coordination, or the hyper ligand. Open coordination site here. Okay, so let's talk about some potential mechanisms for what could happen next. Any thoughts here? Volunteers? Maitali, what do you think? So what about a classical Wacker? What would happen next?
Just the beta hydride.
Beta hydride. Nothing to see here, folks. Straightforward. We're just going to beta hydride eliminate. This is one reasonable possibility. And then you're going to make this peroxide product. You're probably going to have to clean this up, like the palladium zero byproduct that's generated needs to add back in, but this would be the initially generated intermediate. So this is one pathway. What else? Anything else? So based on everything we've covered so far, this is what you should draw. And just to make that clear, so then you would have palladium, you would eventually get to palladium zero this way, the palladium zero would add back in, and this is the reoxidation step. So you don't have copper, you don't have O2 anymore. That's how it's reoxidizing. Okay, so based on what we've covered so far, this is what you should draw. But if you want to get creative, what else could you potentially draw?
Oh, you can do beta hydro on the other side.
Beta hydride on the other side. What's the other side?
There's an open coordination side.
This one, you have to be a little imaginative, and you've got to like draw on your main group chemistry experience. But you could imagine a process that vaguely looks like a pinnacle rearrangement, where you're fragmenting in this kind of way. And the key difference here is if you, and I've tried to set this up, if you were to use a label, you would see evidence of a hydride shift that would be hopefully quite distinctive. And this is exotic. This is not, textbook stuff, but this is indeed. They make this labeled starting material, which ultimately you trace this back to a labeled styrene. They get this product, and they invoke this unusual, non-classical. So again, the point here is even systems like Wacker oxidation that we think are mechanistically well understood and studied, there's still lots of layers to the onion. Rico.
So just like a clarifying question, but you mentioned that like generally the Wacker, like this oxidation with the traditional conditions was like on styrenes, it's like not very clean.
Yeah.
So what about this catalyst system makes it better? Is it like what about this catalyst design system that makes it more amenable for styrenes than the traditional?
Yeah, I think that's a very interesting question. I think one, if you're asking me to sort of speculate based on my reading of the literature, I think one of the things they may have achieved here by using, so it's not that common to use NHC ligands in this type of palladium 2,0 chemistry. I think what they may have done is made it a much worse polymerization catalyst. And so, and this is something interesting to think about in terms of catalyst design. If the cleanliness of your product profile is the main problem, then often you don't need to make the catalyst better at doing what you want, you just need to make it worse at doing what you don't want. So I would speculate that they have achieved making a much worse polymerization catalyst. Palladium 2 is known to be capable of polymerizations of styrenes plus copper plus, I mean, that's kind of a recipe for polymerization type chemistry. Yeah, here.
Sort of related to that for this question, I'm wondering if they did any experiments or had any hypothesizing about OO homolysis and whether or not that might be involved in any way, because having silver around, having palladium around, it's possible to generate this products.
Yeah, it's a good point. I think most of the literature that uses palladium plus TBHP typically invokes 2 electron mechanism, probably because it's palladium and its second row metal prefers not to be open shell. I think if you started throwing in copper salts and other first row metals, then maybe you'd have a more likely chance of making O-center radicals. Like, okay, so moving on, in addition to water as nucleophile, everything we've covered so far is water, or in the last case, TBHP as nucleophile. What else can you get to engage in Wacker type reactivity? So of course, other oxygen-based nucleophiles are compatible, phenols, carboxylic acids, etc. But what we'll cover here are other categories of nucleophiles, first focused on carbon-centered nucleophiles. This example, which is super important and I think underrated example in the history of organometallic chemistry, comes from Suji's lab, where he takes the palladium-2 dichloride COD dimer, reacts it with a malonate, and finds evidence for addition at one of the COD alkenyl carbon atoms. Well, let me actually draw it in a way that's less confusing, so I can at least add to the same carbon as in the product. We form a new carbon-carbon bond. And look at the timing here. This is in the 60s, so this even predates a lot of classical cross-coupling reactions. This is, I think, maybe the first example of a CC bond-mediated process by palladium. This is stoichiometric. What about a catalytic version with carbon nucleophiles? That was developed several decades later by Ross Wiedenhofer's group, first in an intramolecular sense, and then my group developed it into an intermolecular version. The drawings here are a little messy, I realize, but let me kind of walk through here some of Ross's mechanistic insight, the Wiedenhofer group's mechanistic insight from this study, which is interesting. So they performed a series of deuterium labeling experiments after developing this catalytic cyclization that revealed some key features of its mechanism. I'll highlight two of their key findings here. So when they take this alpha-alpha doubly deuterated 1,3-dicarbonyl nucleophile, subject it to their catalytic conditions, they find that deuterium in the product goes to two places. One at the original alpha position, and the other at the alpha position on the other side of the ketone. And that provides evidence to them that there's, after the initial addition, rather than a direct deprotonation, or a direct protonation, there's a chain walking process to generate a new stabilized palladium enolate that then reacts with deuterium in the final event. Then they do an experiment that's very much analogous to the Beckfall and Stille experiments. They doubly deuterate the alkene, tethered alkene, and they ask the question of what about stereochemistry in the product? They find evidence that the palladium and carbon nucleophile are added at opposite faces, consistent with an anti-type carbopalladation mechanism. One theme that you see in these labeling studies is that often you want to get your product into a cyclic form. Why? Because unlike open chain alkyl products, cyclic products allow for accurate, more ready stereochemical assignment. And so almost always when people do these types of deuterium labeling, you either need to make a cyclic product or you need to convert to a cyclic product. And so that goes back to the Stille and Beckfall examples you saw as well. Moving to other categories of nucleophiles, nitrogen-based nucleophiles also participate in early work by Ackermark. Ackermark is one of the godfathers of organopalladium chemistry in Europe, working in Sweden. He mentored the likes of Jan Beckfall and Lou Hegedus. He found that in a stoichiometric sense, you could hoax amine-based nucleophiles to add to alkenes under the action of stoichiometric palladium. And that these intermediates, which are isoluble, could then be reacted in downstream chemistry, for example, with H2 in overall formal hydroamination. But this process could never really, these processes could never really be turned over catalytically. Why? Because your starting material, one of your starting materials, the dialkylamine, is problematic. It's a catalyst poison. And so this pulls your catalyst off cycle. It's very problematic. And so even though it can work in one step, it's highly deactivating in the context of catalysis. So they're only ever able to achieve this stoichiometrically. Years later, through contributions from a number of groups, Hegedus, and the example I've shown here is from Shannon Stahl's lab, this Wacker process was rendered catalytic, and the key finding from the groups involved in this work was that by turning to weakly nucleophilic and weakly coordinating nitrogen nucleophiles, such as cyclic imides, they now have a less poisoning effect on the palladium catalyst. And so these nucleophiles that lie in a pKa range of, I'm just freestyling it here, between 18 and 25, are good candidates for Wacker nucleophiles. And then the key is that they're both less nucleophilic. The key is that they're less nucleophilic, less coordinating, and less and more acidic, so they can be deprotonated with relatively weak base. So we talked about the classical fate of Wacker processes are alkene addition followed by beta hydride elimination. That's this pathway. Oops. But we've also seen snapshots and started to get a sense that alkyl palladium species can also be intercepted with other reaction partners. We saw that in the context of reaction with copper-2 chloride. Other partners that, and we saw that with CO, so that has been developed catalytically with very reactive oxidants, such as iodobenzene diacetate. This can react as an acetate electrophile in a 2,4 cycle to allow alkyl palladium species to be converted to CO bond-containing products. And then you can also intercept, as we saw in that Wiedenhofer example, with a proton as a nucleophile in a process that ends up being overall redox neutral. And so we'll look at a couple examples of that in a moment. And there's some related work from that looks on the surface to be similar, but is kind of mechanistically different from this, where it's a twist on this theme. And that's from today's chemist of the day, who is, anyone want to shout out? Al?
John Wolf.
Don Wolf. Hence my hat. One of my very own chemistry instructors at the University of Michigan, go blue, known for alkene functionalization. And the ligand John Foss, which he discovered as a graduate student with Steve Buchwald, and now bears his name. So what the Wolf group has developed is an interesting twist on this, where they come in with palladium 0, oxidatively add to an organohalide electrophile. That generates a palladium 2 aryl, which is sufficiently pi Lewis acidic that actually it can coordinate an alkene and induce Wacker type or Heck type nucleometallation, migratory insertion, and then subsequently reductive elimination forms the final CC bond. So a form of difunctionalization that's induced by a palladium 2 aryl, as opposed to what we've seen before up until this point, where it's simple palladium 2 salts. Okay, let's look at some intercepting examples here. I promised I wouldn't cover too many from my group, but I realized I had one more here. This might be the last one in the notes. So I talked about this theme of intercepting intermediates, and I gave a preview that we're gonna talk about intercepting with a proton. So here's an example of that. This is from Forrest Michael's group. What they do, they play an interesting trick here. They use a pre-catalyst that is a PNP pincer. And it's doubly cationic, so it's highly pyruvate acidic. It can coordinate to the alkene. It can induce this intramolecularly tethered NH nucleophile to add, but then because it's a pincer ligand, there's no open coordination site necessary for the beta hydride elimination. So it's stuck. It just sits here. It has a beta hydride, hydrogen, you can appreciate that. It has this beta hydrogen present, but it's kind of stuck. And it's so stuck actually that they can just isolate these as intermediates. But what they were able to achieve is that if you treat this with strong acid, so in this case, you can appreciate that you're generating in situ triflic acid or some solvated form of triflic acid, this can protonate off the carbon palladium bond, and then your overall process is redox neutral. At palladium, so all that needs to happen is that it can just directly re-engage the catalytic cycle. There's no oxidation state adjustment needed. So my group applied then a similar concept, slightly different flavor, where we build some of the chelating capabilities that we saw in Forrest Michael case into the substrate. And what happens there is, and you can really give me a hard time if I get any of this wrong. So we have reversible coordination of the substrate. Palladium 2, it makes this, we talked about this as a PNP. This is now a NN pi. Pincer complex. We use some of the same types of nucleophiles, nitrogen-based nucleophiles that we introduced in the context of the Stahl work, carbon-based nucleophiles that we introduced in the context of the Wiedenhofer work, and those will then add in typically these are going with anti-stereochemistry. But that ends up being a little bit of a moot point because it gets ablated the next step and then reacts with proton. The directing group here not only serves to stabilize the intermediate against beta hydride elimination, but also provides a means of controlling the regio selectivity of the addition, because the metallocyclic intermediate here becomes very strained in the opposite. It forms the opposite regiochemical orientation. Okay, we're almost at time here. Let me just give a quick primer to say that beyond just alkenes, other pi systems can engage in analogous addition processes. In the case of alkynes, upon addition, you generate alkenyl palladium species. So with a terminal alkyne, that can be one of two different regiochemical orientations. With 1,3-dienes, and we saw a little bit of a preview of this at the beginning of the class. Upon addition, you generate a pi-al species that then can engage in Leydig substitution chemistry, and this is where we pick things up next time. With allenes, they're unusual, so the above case is a 1,3-diene. Allenes, of course, are 1,2-dienes, and they have two different flavors. If you attack the nucleophile at the internal carbon, you get an alkenyl, you get an al species shown in blue. If you attack a terminal position, you get an alkenyl. And so these have this divergent reactivity profile that can be taken advantage of. For the next class, I will pick things up then and wrap up. I have only a small amount of notes on the heck type. A lot of the themes are things you've seen similar before, but I do want to just scroll ahead to get you all as a homework. So to think about this problem of the day, number 4, which gives you this product, gives you some reaction conditions, and asks you to think about retrosynthetic disconnections that gets you to this product from starting materials of defined formula weight. So make sure what you draw here has a formula weight and molecular formula that's consistent with what the starting material, what the problem of the day set says. So we'll wrap this up next time, which is tomorrow, and then most of the class will focus on Leydig substitution, and then we'll continue exploring more and more facets of catalytic chemistry. Next week, just as a primer, we've got 2 guest lectures. Courtney Roberts on Tuesday, Steve Wisniewski on Thursday. Steve's is actually going to be in person. He's flying out. So that one, we'll want everybody here. Courtney's, I will give you the option. We will have it here if you want to attend here. If you're more comfortable attending via your laptop, you can do that as well. Your call. All right. Thanks, everybody.